All right. Can you see my screen?
Yes.
This is an Excel file. This is something. This is something that I was trying to simulate. For suppose this is a wind turbine foundation where loads were applied at loading eccentricity of 100 meters. I could get, but my program was aborting when I was simulating for pure movement, and I needed the value. So what I did is I have used hyperbolic method. So what hyperbolic method tells is here ultimate load capacity is defined as inverse slope of linear part of y divided by h to y, where h is the load, horizontal load, and y is the displacement and that direction. So in y direction, it is a ratio of y by h to y that will give you a capacity. Now, based on previous analysis, you will get some relation. You have to multiply, and then you will get a capacity that can be used. So let's see here. I had a foundation. So I had applied a load of in terms of displacement of around 1.8 meters at the top. So here at 100 meters loading height, I got the result. So this was perfect. When I was applying the moment load, we see that up to this it went. Up to 1.3 meter it went and then it failed. Then I had to get some load at 1.8 meters. Without that, I will not. I my analysis would have been incomplete. So what I did was I introduced two columns. This was there. This was already there. Displacement, and this is something that I have obtained based on the suggestions of this paper. And then I have plotted y by h in y-axis and y in x-axis. So this is what I have plotted. So this is y by h in y-axis, and this is y in x-axis. And then you see, based on hyperbolic method, means y by h. Suppose some linear part, you have to find the slope in some linear part. When you do that, you'll be getting a capacity, capacity based on hyperbolic method, and you already have a capacity based on your program that we has already completed. So this is the capacity. So this is the capacity. So we'll find a ratio of this hyperbolic capacity, the capacity that you have got based on hyperbolic method and your actual capacity. And then you will get a calibration factor. So this calibration factor has to be used for the programs which have terminated. So what I have done is, for me, this program has terminated, has gone till 1.3 meters of displacement. So what I did is, I have used the same hyperbolic method. This H is the calibration factor that I have obtained from the previous analysis that has run completely. And then I have plotted this y by h to h. And then what I did is I got a capacity, hyperbolic capacity. And what I did, I just multiplied this with this calibration factor, and I got the new ultimate capacity. That is one way when you just cannot run or get complete run of the analysis aborts in between. So hyperbolic method comes handy. So this is one part that I thought I would be showing. Now the second part is some programs we told that will be running using Drucker-Prager model and uh, CamClay model. So while I was trying to run the CamClay model, I tried to find many papers, and then one I got, which was something similar to 3D. 2D, there are many problems, but I preferred handling things in 3D. But I was getting continuously errors and all, so I could not complete that. So I'll again have a session for around 10, 20, 25 minutes tomorrow with CamClay model. So today what I'll do is I'll discuss about Drucker-Prager and CamClay model, what are the basis, and then we'll run a simulation on modified Drucker-Prager pattern using modified Drucker-Prager parameters. So a bit of continuum mechanics fundamental is required. This is something that we have discussed while Moore, Coulomb, and Tresca failure criteria. So this is suppose a soil element, and it has got six faces, and along six faces there are normal components and there are shear components. So the forces those are acting perpendicular to these faces, they are called normal forces, and these are called shear stresses. So the planes where these shear stresses are not there, so it is a principal plane. So in this case, we have shear stresses. Yes, sigma 1 means it is acting in one plane in one direction, or in x plane in one direction. So sigma 1 can also be here represented as sigma xx. So likewise, sigma 2 to sigma yy, and tau 1 2 is tau xy, tau 1 3 is tau x. These things we have already explained. So the stress at any point can be explained or represented in terms of tensor. So now to operate on tensor, we need to calculate invariance. So these invariants, they do not vary with the coordinate system, and we can determine the stress invariance. Like for this first invariant, we represent it by I1. This is nothing but the diagonal terms, summation of the diagonal terms. And I2 is nothing but the minor of sigma 1 plus minor of sigma 2 plus minor of sigma 3. You add these things, you will get I2, and the determinant of all matrix is I3. So these are some invariants, stress invariants. Now, likewise, for the tensor, there are some more invariants. So J1 is like sigma 1 like I1. It is sigma 1 plus sigma 2 plus sigma 3. So these are the basic things, basic invariants that we have already studied in continuum mechanics. So now, when we have an element that undergoes stress, so we can decompose it. Suppose this is a stress matrix, so we can decompose it with reference to deviator stress and mean stress or hydrostatic stress. So this mean stress can be
Sir,
also, yes,
sir, these J1, J2, J3 are like derivative stress invariants.
yes.
But sir, isn't J1 it remains zero? I think always.
J1 would be 0. We'll see later.
Okay. Sir.
When you subtract this, iska, when you operate, so it will become 0. So here you see J1D is the derivative stress invariant, and this becomes 0. This we are going to come.
Okay, okay. You are represented by J1D. Okay, okay.
J1, yes. So this is the deviatoric stress plus this is the hydrostatic stress. If you add these two, this is the total stress at any point. Now, what we do is we bring the deviatoric stress to the left and we bring this to the right, and the matrix that we are in the form that we are going to get is this. So here the first invariant, this is the first invariant of Dimitrov stress. This was the invariant of stress tensor. J1, J2, J3, these are invariant of stress tensor, and J1D, J2D, and these are for Dimitrov stress. So if you just do S11 plus S22 plus S33, it is nothing but sigma 11 plus sigma 22 plus sigma 33 minus 3p. So that way this is equal to 0. Likewise, you get J2D and J3. These are the basics that we just study in initial part of container mechanics. Now, to some extent, we have their uses while we study different soil models. Whatever we have, I have taken is from mainly two books. One is application of finite element in geotechnical engineering, and the other one is Sam Helvani. So this is the modified Dracal model is also called a CAP model, and it is capable of considering the effect of stress history, stress path, dilatancy, and the effect of intermediate principal stress. So this has been represented in PT space. Here you see this is the shear failure or failure surface. This is an elliptical cap, and in between this failure surface and the elliptical cap there is a smooth transition. So this is also called transition surface. So the Drucker-Pragal or cap plasticity model consists of three parts. One is this shear failure surface, one is this transition surface, and the other one is this cap. So as the load is applied on any material, the uh, material always hooks low, and within this elasticity limit, the strain or stress calculations are done from proportionality. However, when the load exceeds the yield point or the onset of the plastic behavior can be determined using the modified Drucker-Pragal surface or this cap yield surface. So this, if I have to define, or the failure surface of Drucker-Pragal is defined, or the yield surface is defined by F is equal to T minus P tan beta minus T. So T is nothing but we see MIT plot PT space and all, so that is T. And here we'll see the remaining things. So this cap is of elliptical shape. So here these components R is the eccentricity of the ellipse in PT space, and the cap surface is dependent on the third invariant. So it takes so this R represents this, that it is dependent on this third invariant. So it can consider stress dependency also as compared to mole column model. It will be able to take care of this stress dependency. And this is the expression for cap yield surface. Fc is equal to P under root of P minus PA RT, this expression. So here we'll see one by one what are the parameters and how we can get from the laboratory tests. So here, firstly, the cap has a rule. The cap surface hardens or softens as a function of volumetric strain depending on how the load is applied, if and the nature of the soil. When the stress causes yielding on the cap, the volumetric plastic strain or compaction is experienced, and it leads to hardening. And when there is some contraction, so it leads to softening due to volumetric plastic dilation. So this PA you see in this diagram here, this is the transition part, this is PA, this end is PB. So Pa can be expressed as Pb minus R into d. R is the eccentricity, and this term, we'll see eventually how to determine d by 1 plus R10 beta. So the volumetric plastic strain, there is a term. It is again a function of Pb, and it can be easily obtained from isotropic consolidation test with several loading and unloading cycles. So if we draw from the consolidation test, from this equation, if we vary this P and we keep on changing the magnitude of P, so we'll be getting a lot of data set, and from there we'll be getting the volumetric plastic strain. Here this P naught is the current pressure, and P dash C is pre-consolidation pressure. Lambda, kappa and lambda are the slopes of NC line or normal consolidation line, and loading unloading line. CC and CS are compression and swelling indices. They can be obtained from this consolidation tests, and this lambda can be determined using CC as CC by ln10, and same kappa can be determined. So these are the parameters which can be determined based on consolidation tests, and this flow rule dictates how, upon application of load, the plasticity behavior is going to be there in terms of expansion of the failure surface. You see, this is the direction where the cap is expanding under the application of load or under particular strain level. So this is the direction where the shear failure is expanding, or the surface is expanding. So when it expands, the flow rule or flow potential function for the cap is given by this parameter P minus Pa to RT1 minus this term. So, and for this surface, this shear failure surface, it is, and the transition surface, both the surfaces are combined together, so it is given by this expression. So these are basically governing the flow. These are used to determine the plastic strains, or through iterations under when it exceeds yield, how the strains are calculated at each increment. So to determine these parameters from laboratory, results of at least 3 triaxial compaction tests are used to determine D and beta. So the at failure condition, the results can be plotted in PT plane. T is nothing but sigma 1 minus sigma 3. We know that. And P is the mean pressure, is sigma 1 plus 2 sigma 3 by 3, where sigma 2 is considered as sigma 3 in isotropic in this thing. So when you plot this in PT space based on the triaxial tests, based on either compression test, CD or CU test, you'll be getting the point. So wherever the intercept is going to be there in PT space, so that will be D, this term D, and the angle would be, angle of slope of this line would be beta. Alternatively, you can also, there is a correlation between beta and phi. Phi is something that we get from Moore Coulomb theory. So 10 beta is 6 sin phi dash by 3 minus sin phi dash. This is a correlation between this friction angle that is used in Drucker-Plagal model with Moore Coulomb friction angle. And this D is the intercept that we got in PT space, that is directly correlatable with the cohesion that is obtained from Moore Coulomb test. So this is again add in C cos phi dash by 3 minus sin phi dash. So these are the two terms that we can, it also indicates that if we have Moore Coulomb model, we can convert them into Drucker-Prager model as well and do some comparative study. R has got some values. So in general, the eccentricity is assumed to be zero point 0.4. This is a standard value. And initial strain in the initial stress of the cap hardening is initial strain at cap hardening. Sorry, the cap hardening curve is zero, cause during as the load is applied. So load is applied gradually till elastic point, and then gradually as it is increased, so the plastic deformations takes place. So it is assumed that the initial strain is zero. So epsilon zero is zero, and alpha is a factor that controls the curvature of the curves cap. So it is generally kept as it's from 0.01 to zero point 0.05. Usually it is adopted as 0.01, and the value of k can be used determined using this 3 minus sin phi by 3 plus sin phi, this friction angle. Now I have like taken some values from Sam Helwani. These values have been taken from some problem in Sam Helwani, and I have tried to simulate a pile foundation and how these loads are applied, means under several loading conditions. So this is a pile foundation on which we have already worked. So there we have already given some loads. Let's see what load was given. So it was already, we have already performed this, and then here some lateral load is also applied. So this was some exercise that we have done before. So here what we'll do is, here we have used this Moore Coulomb model. So today we are going to use Drucker-Prager material model and see how the response is. I'll just copy this model and then name it MDP, modified Drucker-Prager, or the cap model. So here my density is kg per meter cube 1923. Density is there, and then modulus of elasticity and Poisson's ratio. Poisson's ratio is 0.28. Material cohesion D is, now I'll, from plasticity parameters, I'll choose cap plasticity. It represents Drucker-Prager model, and my material cohesion is 10 to the power minus 5 and E minus 5. Angle of friction is beta. You see, do not get confused with this angle of friction beta as 55.7, because this is, in general, when we talk about angle of friction, we denote it by phi, and it is quite a high value. So when it is beta, it is okay. 55.7. Cap eccentricity is 0.4. Initial surface position is 0. Transition surface radius all alpha is 0.5. And flow stress ratio is 1. These values are generally used in many problems in Sam Helwani's book, so you can get it from there. And now I have to define this hardening parameters. So these are calculated based on the uh, slopes, kappa, lambda, and all. So this we have these values directly. Otherwise, if based on experiment you want to calculate, so this can be calculated from this equation also. So generally I have these values, so I'll straightway use this. And so this is something that has been used. So density has been used. Modulus of elasticity, cap plasticity, cap hardening, everything has been used, and the soil has already been assigned. So I'll create a new job. Trial. Continue. The usual thing is, if you see in 3D space, it is circular and all is elliptical from the profile. So what happens is it gives you easier convergence as compared to Moore Coulomb theory, Moore Coulomb material model. So in this model, the pile was subjected to a vertical load of minus or downward 3 kilonewton downward, and the lateral load was applied as 30 kilonewton. So this is quite small. I'll just increase it to some more higher values. Then I'll relearn the things. All right, so this has completed. So we can see the results. The load that we have applied was very small. So this is something that has been there. So from there we can determine the load deformation, or also you can see the plastic strain. This is how the plastic strain has been generated. The base there is some strain, and then at the top. Likewise, you can conduct a parametric study of how these behavioral plastic strain and soil deformation and other things are between Moore Coulomb and Drucker-Plager material models. So this is one part. Now I was trying to simulate this paper with modified CAMCLE model. So I was getting some errors which I could not solve before the class. So we'll meet tomorrow for some half an hour, and then We'll discuss about the theory of Chemclay model and we'll solve one or two problems. I'll try to have a problem based on 3D, and if at all 3D is not possible, so we'll go ahead with 2D problems. So, is that fine? Is that okay?
It's okay, but if possible, just a small explanation about the plastic failure calculation for the hardening gap.
For cap model? Okay.
Yes,
Okay, so I'll try to do that tomorrow.
for plasticity and the failure will be
Mhm.
good. Wallah.
Here, if you, I'll just stop this recording.